All right, welcome back. So, last video, we dived into chapter three. So, it's time to keep going. We're gonna move to the next section, which is so chapter three is all about model evaluation. This is a growing field in machine learning right now. It's hard to tell whether or not one model is doing better than the other, and that's going to continue to be a big challenge in this space. So one of the biggest growing subfields in this space is developing the technology to determine how a model is performing. So this chapter has been all about that. There's a lot of really complex mathematical concepts that you need to know in order to determine how a model performs. And models can perform better or worse in a lot of different ways. One of the ways that a model can perform better or worse is the entropy of the model. How much information does it carry per token? And even that, the idea of it performing better or worse is kind of complicated as well, because there are some uh, situations where you want it to have a lot of entropy, each token, but there are situations where you don't want it to have a lot of entropy if you want the answer to be more predictable, for example. So this is a very heavy, meaty chapter with um, a lot of big mathematical concepts, entropy, cross entropy, and units of entropy, perplexity. Um, so lots of big, big words and big equations as well. We can see an example of one right here. So I kind of the author says for some of this you can just skip it. I'm getting trying to get a sense of it. I now one mistake I've been doing that I think I'm going to try to not do going forward is I've been using ChatGPT for O1 Pro mode to get a sense of the mathematics of this chapter, and it's just way too slow. It takes minutes for it to think through and provide a response. So I think going forward, I'll use 4.0, and then if the answer's leaving a lot to be desired, oh, you know what? It used to have reason. Okay, yeah, I'll use 4.0, and if the answer's leaving a lot to be desired, then I'll just switch over. I'll have it to reason with O1 like that. That way it'll spit out the answers really fast. And 4.0 is still a pretty solid model. All right, so next section is exact evaluation. When evaluating models' performance, it's important to differentiate between exact and subjective evaluation. Exact evaluation produces judgment without ambiguity. For example, if the answer to a multiple choice question is A and you pick B, your answer is wrong. There's no ambiguity around that. On the other hand, essay grading is subjective. An essay score depends on who grades the essay. The same person, if asked twice sometime apart, can give the same essay different scores. And not only that, in education these days, it's often graded by a grading system, an artificial intelligence, or even worse than that, just a robot that has no idea. Like they've actually done uh, testing on it where the coherence of what you write does not matter at all, and it just comes down to word choice. What's the the Noam Chomsky sentence. So the Noam Chomsky sentence is something to do with, yeah, colorless green ideas sleep furiously. You would get an A plus for writing that on a essay exam that's graded by a machine, because it's got perfect syntax, semantics, sentence structure. Everything about that is absolutely perfect. But a colorless green idea, it can't be green if it's colorless. And how does it sleep furiously? It's asleep. There's no way to do that in a furious way. I guess maybe if you're having a dream, but ideas don't have color at all, so it can't even be colorless because it's not a medium that accepts a color. So this is where we're at today. If you want to pass a essay grading, colorless green ideas sleep furiously, and oh man, to this day it burns me up inside. I took uh, a entry an assessment to go to a community college, and they wanted you to read a they wanted you to write an essay to persuade someone of a position on an argument. And I forget what the argument was, but you could take either position of the argument, but the goal it said was to just be as persuasive as possible to the person reading it, is how I interpreted it. But obviously, I interpreted it very wrong because there was no person reading it. So I just wrote in this really like kind of creative writing, persuasive way, and I used like one of the things I like to do is like write well, like really vary up my sentence lengths and write like one word sentences and like kind of get a little bit creative, like use em dashes and like use kind of like unusual characters and stuff to try to like really be persuasive and emphasize and like make things look a little bit unusual. And I got a 3 on it out of 5 or something like that, or a 4 out of 5 because it didn't follow the because it was read by an AI and it didn't follow the exact colorless green ideas sleep furiously syntax that it was looking for. And oh man, it still burns me up to this day. Yeah, so an essay score depends on who grades the essay. The same person, if asked twice sometime apart, can give the same essay different scores. Essay grading can become more exact with clear grading guidelines. As you'll see in the next section, AI as a judge is subjective. The evaluation results can change based on the judge model and the prompt. I'll cover 2 evaluation approaches that produce exact scores: functional correctness and similarity measurements against reference data. Note that this section focuses on evaluating open-ended responses, arbitrary text generation, as opposed to closed-ended responses, such as classification. This is not because foundation models aren't being used for close-ended tasks. In fact, many foundation model systems have at least a classification component, typically for intent classification or scoring. This section focuses on open-ended evaluation because closed-ended evaluation is already well understood. Functional correctness. Functional correctness evaluation means evaluating a system based on whether it performs the intended functionality. For example, if you ask a model to create a website, does the generated website meet your requirements? If you ask a model to make a reservation at a certain restaurant, does the model succeed? Functional correctness is the ultimate metric for evaluating the performance of any application, as it measures whether your application does what it's intended to do. However, functional correctness isn't always straightforward to measure, and its measurement can't be easily automated. Code generation is an example of a task where functional correctness measurements can be automated. Functional correctness in coding is sometimes execution accuracy. Say you ask the model to write a Python function, GCD, num1, num2, greatest common denominator, to find the greatest common denominator, GCD, of 2 numbers, number 1 and number 2, defined as variables num1 and num2. The generated code can then be input into a Python interpreter to check whether the code is valid, and if it is, whether it outputs the correct result of a given pair, num1, num2. For example, given the pair num1 equals 15, num2 equals 20, if the greatest common denominator between the two should be 5. If the function GCD 1520 doesn't return 5, the correct answer, you know that the function is wrong. Long before AI was used for writing code, automatically verifying code's functional correctness was standard practice in software engineering. Code is typically validated with unit tests, where code is executed in different scenarios to ensure that it generates the expected outputs. Functional correctness evaluation is how coding platforms like LeetCode and HackerRank validate the submitted solutions. Popular benchmarks for evaluating AI code's generation capabilities, such as OpenAI's Human Eval and Google's MPBB, mostly basic Python problems dataset. Oh, that'd be interesting. Um, I feel like uh, I feel like I should be able to get these right. Um, so here's the yeah. Cool. I like this. And then it gives you the answer. Oh, this is good. This is good. You could put this data set into Anki, and it's basically in the same format already of what to write Anki cards. Oh, this is great. You got near 1,000 Anki cards. Wow. Okay. Well, let's do it. Um, what is the flashcard system ANKI? Does it have a way of creating cards programmatically using something like Python? Okay. Show me a brief example of a script that creates cards using a JSON payload. All right, so 4.0 is a lot faster. Yeah, so here we go. Let's do this. All right. So, uh, so this is the MPBB, uh, mostly basic Python problems data set. Okay. Okay. Okay, so yeah, all I gotta do is change front and then the tags I gotta change. But I gotta change this text here to front, and then I've gotta change this code here to back. Um, and that's all I gotta do. Okay. Uh, there we go. I have this folder already called Anki Automation. Um, and then I should have a virtual environment in there. Uh, so, oh, do I not? Oh, yeah, I do. It's right there. So, uh, then uh, scripts. Oops. Scripts activate. Perfect. Okay, now I have IPython 3 because it's a requirement. Oh, or maybe I just have IPython. Oh, well, now I can get it though. Okay, uh, so pip install upgrade pip. All right, pip install IPython. All right. Oops. Uh-oh. Something's. Oh, it's already satisfied, but yet it's not. Uh, normal packages is not writable, already satisfied, but yet it doesn't work. What the heck? Okay. Let me go to bash. Okay. Source bin activate. It's probably because I installed it in. Yeah, it's probably because I installed it in the uh, Windows subsystem for Linux, but not in. So like when you activate Venv scripts, there's different crap in there than when you activate Venv bin in Windows subsystem for Linux. And maybe but I don't know why it would say that it's already installed then, but whatever, forget about it. It really doesn't matter. Okay, so yeah, let's take this and let's do an exit here, and we'll do a code dot. Get that open in VS Code. All right. All right, now get all this. So select all. Uh, New file. Okay, and now we're going to replace this with front. Okay, and then we'll replace this with back. Replace the, yeah, code like that with back. All right, and then we need to put this all in one uh, payload. So we have to add. Oh, yeah. So we've got a challenge test list at the end. So I think we can change that to tags. Yeah, and then just leave that empty. Oh, but there's a bunch of crazy crap in here. Test setup code. Oh, there's a bunch of extra ones. Oh, there's some with extra ones. Well, shoot. I'm sorry. I'm way off track and wasting time. That might be good to go and do later. Honestly, there's probably better resources out there, but oh, and I could even let me do this. Let's say clean this up to be okay. Now uh, rewrite the script to make cards, but make the cards using this data. Ah, crap. Okay, well, how many lines do I get? Oh, man. Okay, so let's do a 4.0. So 4.0 Pro, okay, and then we're gonna say, home. Okay, rewrite the script using this data. Oh, an error. Okay. Oh, yeah, still an error. Okay, uh, okay. Um, I want you to create a um, Anki script to build flashcards to help me learn Python. I will give you the data to use to make the cards out of when you are ready. Or actually, no, I can just, yeah, let me just upload a file. Uh, Python challenges for flashcards. Okay. See the attached file for the data I want you to make cards from. Uh, oh shit, it has to. I keep forgetting that it has to be an image. Um, uh, all right. Um, find you can find the data. Yeah. So see the link. Uh, see this link to find the data I want you to make cards. Perfect. Oh, and the link, not the data. There we go. All right. So sorry about that big tangent. Probably would be best to scrap this, but anyways, moving on. So, popular benchmarks for evaluating AI's code generation capabilities, such as OpenAI's Human Eval and Google's NPBB, mostly basic Python problems dataset, use functional correctness as their metrics. Benchmarks for text to SQL, generating SQL queries from natural languages, like Spider Bird SQL, big bench for large scale database grounded text to SQL evaluation, and Wiki SQL also rely on functional correctness. A benchmark problem comes with a set of test cases. Each test case consists of a scenario the code should run and the expected output for that scenario. Here's an example of a problem and its test cases in Human Eval. So the problem is yeah. So this is from Human Eval. So not the one that we're making cards out of. Okay. All right, and then test cases. There we go. So when evaluating a model for each problem, a number of code sample. A really good way to learn Python, by the way, and I'll just show this if in case anyone's watching that wants to learn Python and doesn't know. It's called learning Python the hard way. So the hard way is actually the easy way, because it puts everything in your fingers, um, which really sets you up for success later on. But it's called the hard way because you're going to make so many mistakes, and you can use IPython, but even that, basically you want it to be as much of a tedious grind as you can make it. um, you want your code to work, but it's called doing it the hard way for a reason. So basically all it is you're just typing it in as if you're doing Mavis Beacon. And look, already I did not capitalize the L. What's going to happen? Boom. So you like the idea is you want to see this stuff happen, and you want to be like typing import. Okay, there is a capital L. Now it works, right? So if you're watching this channel and you want to learn Python, I definitely recommend uh, doing things the hard way. And whenever you see an example like this, just as if you're doing um, a typing exercise. Type everything out. Tedious, boring. I mean, you're trying to become a programmer, right? Like, are you aware of the stereotypes of programmers? Like, this is what you're saying you want to do, right? So like, this is probably, in my opinion, the best way to learn Python is to learn it the hard way and just as if things were a random sequence of characters, type everything out, character by character, and do not make any mistakes at all. And you can see oh, okay, never mind. Yeah, so like, yeah, so you can see, oh, is this going to error out? I didn't close the triple quotes. Nope, it doesn't because it's a multi-line string. So it really helps you to learn what your intuitions are, um, about whether something's going to work or not, and see if they're right or wrong. You can do so much immediate. This is what I think is what happens versus this is what actually happens if you're using the interpreter. It's, in my opinion, the absolute best way to learn is to spend as much time as you can in the interpreter and just type. That's basically what you're claiming you want to do if you're studying programming. You're trying to be Boris um, from James Bond, GoldenEye. So like, there we go. There we go, and it all goes through there. So that's yeah, and we can see you can get a sense. So there we go. That's the definition. Um, and then I'll just do the next one. And then you get to play with them, right? Like once the objects are built, uh, you actually get to play around, which is fun. So this is definitely the hard way. We can see nothing I'm doing is abbreviated, and this takes a long time. But the hard way ends up being the easy way after a while. And we can see we've got an invalid syntax here. And we can see I spelled asset rather than assert. So right there, that's a pretty critical skill. And we can see unexpected indent. I have to start with this line here. And there we go. It all goes through. So see how valuable that is? It's like, you're like, imagine you write a whole script and you have these little errors and like, it's like, oh, what went wrong? And it gets frustrating. Like, this is what you're claiming you want to do when you claim you want to learn Python. You want to nitpick over every little tiny pixel on the screen and make sure that you didn't leave out the R or you didn't fail to capitalize the L. Like that's what you're claiming you want to do when you claim you want to learn Python. So the best way to do it is to do it the hard way and um, you forget about your fancy IDEs for now. Just even use Notepad and then copy paste it over. Like make it hard on yourself because you'll make it easier later on. It's like you can think of it like weight training. But anyways, don't need to keep doing that. When evaluating a model for each a problem, a model of code samples denoted as K are generated. A model solves a problem if any of the K code samples it generated pass all of that problem's test cases. The final score called pass K, yes, with an at sign there, is the fraction of the solved problems out of all problems. And I'll do an audio check and see that it's not recording. Okay, it is. Perfect. Um, if there are 10 problems and a model solves 5 with k equals 3, then that model's pass at 3 score is 50%. So this is pretty confusing. So the final score is called pass at k, and it's the fraction of the solved problems out of all problems. So the k stands for stands for the solved problems. So if there are 10 problems in a model, wait, what? All right, let's give me a clearer explanation of the let's get this from and let's just use the fast one. Um, create a new chat. We'll create 4.0. We'll say, give me a clearer explanation of uh, pass at k. Okay. And then let me reread this again because it's going over my head. When evaluating a model for each problem, a number of code examples denoted as k. Okay, so the number of code examples are generated. So in the example here, there were 3 code examples. A model solves a problem if any of the k code examples it generated pass all of that problem's test cases. The final score, called pass at k, is the fraction of the solved problems out of all problems. If there are 10 problems and a model solves 5 with k equals 3, is, oh, I see. So there are 10 problems and these are code problems. So basically you can solve these problems by writing code. So the model solves 5 of those problems, and for each of those problems it provides 3 code examples that contain the solutions. Wait, what? Okay, so if there are 10 problems and a model solves 5 with k equals 3, then that model's pass at 3 score is 50%. The more code samples a model generates, the more chance the model has at solving each problem. Hence, the greater the final score. This means that in expectation, pass at 1 score should be lower than pass at 3, which in turn should be lower than pass at 10. Another category of tasks whose functional correctness can be automatically generated is game bots. If you create a bot to play Tetris, you can tell how good the bot is by the score it gets. Tasks with measurable objectives can typically be evaluated using functional correctness. For example, if you ask AI to schedule your workloads to optimize energy consumption, the AI's performance can be measured by how much energy it saves. All right, so I'm going to move the bookmark. And there was a major tangent here, unfortunately, but uh, okay, so there we go. Back to ChatGPT. Okay, so here it is explained simply. So pass at K is a way to measure how well a model performs at solving coding problems. Here's how it works. Number one, generating solutions. When given a problem, the model generates K different code samples as possible solutions. So I was right. Okay, checking solutions. If at least one of these K samples passes all test cases, the problem is considered solved. Okay, so it gets 3 tries. Well, it gets K tries. Final score calculation. Percentage at K, pass at K is the percentage of problems that the model successfully solves when generating K solutions. For example, suppose a model is tested on 10 coding problems. It generates 3 solutions per problem. If at least one of these 3 solutions works for 5 out of 10 problems, the pass at 3 score, so attempts, K stands for attempts, is 50%. So if you get it by the third try, then you passed the challenge. And if you get half of the questions right in at least 3 tries, your score is 50%, even though for some it might have taken you all 3 of those tries. So a general rule is that the higher the K, the more chances the model has to find the correct solution. So pass at 1 is a better score than pass at 3, is a better score than pass at 10, meaning pass at 10 will usually be the highest. Okay, so that's interesting. So that's interesting. Tell me the practical implications of that. So like, why does this matter? Like, put briefly and simply, like, I guess, like, yeah, it's interesting because if you have a pass at 10 and then it gets all the problems right, but it takes 10 attempts, that's a much different outcome than a pass at 1 that only gets half the problems right, but now you're saving so much money and time because it only gets one shot, and maybe you're okay with it only getting half of them right, but you just don't have the money for it to take so many attempts. Yeah, so computational speed and cost. Yeah, so it's a trade-off in speed and accuracy. Yeah. Yeah, so like oftentimes to pass a test, you don't need to get 100%. So if you so it's more important that it's a trade-off between speed and accuracy and resource consumption and likelihood of passing the test. So all right, so next section is similarity measurements against reference data. If the task you oh wait, I don't think I read uh, no, I didn't read this part yet. Another category of tasks whose functional correctness can be automatically evaluated is game bots. If you create a bot to play Tetris, you can tell how good the bot is by the score it gets. Tasks with measurable objectives can typically be evaluated using functional correctness. For example, if you ask AI to schedule your workloads to optimize energy consumption, The AI's performance can be measured by how much energy it saves. All right, now time for the next section, similarity measurements against reference data. If the task you care about can't be automatically evaluated using functional correctness, one common approach is to evaluate AI's outputs against reference data. For example, if you ask a model to translate a sentence from French to English, you can evaluate the generated English translation against the correct English translation. Each example in the reference data follows the format input, comma, reference responses. An input can have multiple reference responses, such as multiple possible English translations of a French sentence. Reference responses are also called ground truths or canonical responses. Metrics that require references are reference-based, and metrics that don't are reference-free. Since this evaluation approach requires reference data, it's bottlenecked by how much and how fast reference data can be generated. Reference data is generated typically by humans and increasingly by AIs. Using human-generated data as the reference means that we treat human performance as the gold standard and AI's performance as measured against human performance. Human-generated data can be expensive and time-consuming to generate, leading many to use AI to generate reference data instead. AI-generated data might still need human reviews, but the labor needed to review it is much less than the labor needed to generate reference data from scratch. Generated responses that are more similar to the reference responses are considered better. There are four ways to measure the similarity between two open-ended texts. Number one, asking an evaluator to make the judgment whether two texts are the same. TEXT. Number two, exact match, whether the generated response matches one of the reference responses exactly. Number three, lexical similarity, how similar the generated response looks to the preferred responses. And number four, semantic similarity, how close the generated response is to the reference responses in meaning semantics, in meaning semantics. Two responses can be compared by human evaluators or AI evaluators. AI evaluators are increasingly common and will be the focus of the next section. This section focuses on hand-designed metrics, exact match, a lexical similarity, and semantic similarity. Scores by exact matching are binary, match or not, whereas the other two scores are on a sliding scale, such as between 0 and 1 or in between -1 and 1. Despite the ease of use and flexibility of the AI as a judge approach, hand-designed similarity measurements are still widely used in the industry for their exact nature. Note, this section discusses how you can use similarity measurements to evaluate the quality of a generated output. However, you can also use similarity measurements for many other use cases, including but not limited to the following: retrieval and search. Find items similar to a query. Ranking. Rank items based on how similar they are to a query. Clustering. Cluster items based on how similar they are to each other. Anomaly detection. Detect items that are the least similar to the rest. Data deduplication. Remove items that are too similar to other items. Techniques discovered in this section will come up again throughout the book. All right, so the next section goes into all these different ways of measuring the similarity between two open-ended texts. The first way is exact match. Oops. It is considered an exact match if the generated response matches one of the reference responses exactly. Exact matching works for tasks that expect short, exact responses, such as simple math problems, common knowledge queries, and trivia-style questions. Here are examples of inputs that have short, exact responses. What's 2 plus 3? Who was the first woman to win a Nobel Prize? What's my current account balance? Fill in the blank. Paris is to France like blank is to England. There are variations to matching that take into account formatting issues. One variation is to accept any output that contains the reference response as a match. Consider the question, what is 2 plus 3? The reference response is 5. This variation accepts all outputs that contain 5, including the answer is 5, and 2 plus 3 is 5. However, this variation can sometimes lead to the wrong solution being accepted. Consider the question, what year was Anne Frank born? Anne Frank was born June 12th, 1929. So the correct response is 1929. If the model outputs September 12th, 1929, the correct year is included in the output, but the output is factually wrong. Um, yeah, it's also a little bit wrong if the model would output June 12th, 1929, because it was asked what year Anne Frank was born. It wasn't asked for the full birth date, so I wonder if that's taken into account. Beyond simple tasks, exact match rarely works. Given the original French sentence, comment ça va, um, there are multiple possible English translations, such as how are you, how is everything, and how are you doing. If the reference data contains only these three translations and a model generates how's it going, the model's response will be marked as wrong. The longer and more complex the original text, the more possible translations there are. It's impossible to create an exhaustive set of possible responses for an input. For complex tasks, lexical similarity and semantic similarity work better. And the other thing to note is um, like this kind of locks the model into producing English responses. Like one of the coolest things you can do with the model in my opinion, is go into conversational mode. And I don't know, I select Pro when I do that. I think Advanced Voice has its own model, but this is one of the coolest things you can do. Hola, ¿cómo estás?
Hola, Graham. Estoy bien, gracias. ¿Y tú cómo estás?
Bien, gracias.
Qué bien. ¿En qué te puedo ayudar hoy?
Estoy, damn it.
¿Sí? Te escucho. ¿Qué tienes en mente?
Estoy reading a book.
Eso suena genial. ¿Qué libro estás leyendo?
Damn it.
Qué bien.
So I don't know Spanish. I studied it for 5 years in school, which is a Gelman amnesia. I basically received no education in school. If that's how good I am in Spanish, if I studied for 5 years, I all my other subjects I'm probably equally as bad. But like, isn't this cool? Like, you get the transcript afterwards. Bien, yeah, so Libro. So this probably has to do with, and the thing is, like, you can get more sophisticated with it. Okay, thanks for helping me out with this. Obviously, I'm learning Spanish. Obviously, I know like basically nothing. Teach me the phrase "I am reading a book."
Of course. In Spanish, you can say, estoy leyendo un libro.
Estoy leyendo libro.
Casi perfecto. Solo añade el un. Estoy leyendo un libro. Bien hecho.
Cool. Now help me out to learn a good response to what you just said.
Sure, you can respond with, Gracias, estoy aprendiendo. This means thanks, I'm learning.
Gracias, estoy aprendiendo.
Exacto, you're doing great. Keep it up.
All right, keep teaching me Spanish, and I'll give me something I can say if I'm just completely like lost for words.
Absolutely. If you're lost for words, you can say, no entiendo. That means, I don't understand. It's a handy phrase.
No entiendo.
Perfecto. That's exactly right. You're picking it up quickly.
All right, start a conversation with me in Spanish, and I'll respond no entiendo if I don't understand.
Claro, vamos a intentarlo. ¿Qué te gusta hacer en tu tiempo libre?
No entiendo.
Está bien. Te pregunté. What do you like to do in your free time? You can say, ¿qué te gusta hacer en tu tiempo libre?
¿Qué te gusta usted tiempo libre?
Casi. La frase correcta es,
My guidelines won't let me talk about that.
All right.
Can I
So
help
so
you
you
with?
can see like that's one of the most in my opinion, that's one of the most powerful things you can do with a model these days, advanced conversational mode. And we saw in reading this book, the model's not so good with other languages, but it's really good with German and I think like actual Russian, not Ukrainian. Um, so that gives you a good basis for navigating the world. You can probably learn Ukrainian easier if you know Russian first. And then German is a widely spoken language. Um, and then we saw it can do Spanish. It can do lots of different languages. Like if you don't know any of that language, I think it's a good tool. But anyways, moving on. Okay. So the longer and more complex the original text, the more possible translations there are. It's impossible to create an exhaustive set of possible responses for an input. For complex tasks, lexical similarity and semantic similarity work better. Lexical similarity measures how much two texts overlap. You can do this by first breaking each text into smaller tokens. In its simplest form, lexical similarity can be measured by counting how many tokens two texts have in common. As an example, consider the reference response, my cats scare the mice, and two generated responses. My cats eat the mice. Cats and mice fight all the time. Assume that each word is a token. If you count overlapping of individual words only, response A contains 4 out of 5 words in the reference response. The similarity score is 80%, whereas response B contains only 3 out of 5. The similarity score is 60%. Response A is therefore considered more similar to the reference response. One way to measure lexical similarity is approximate string matching, known colloquially as fuzzy matching. It measures the similarity between two texts by counting how many edits it need to convert from one text to another, a number called edit distance. The usual three edit operations are deletion. So Brad, the R would be deleted, and it would be bad. Insertion, bad could be changed to barred, and substitution. Bad could be changed to bed by substituting an A for an E. Some fuzzy matchers also treat transposition, swapping two letters. For example, mats to mast to be an edit. However, some fuzzy matchers treat the same transposition as two edit operations, one deletion and one insertion. For example, bad is one edit to barred and three edits to cache, so bad is considered more similar to barred than to cache. Another way to measure lexical similarity is n-gram similarity, measured based on the overlapping of sequence tokens, n-grams instead of n tokens. A n-gram unigram is a token. A 2-gram bigram is a set of two tokens. My cats scare the mice consists of 4 bigrams. My cats scare the, and the mice. You can measure what percentage of n-grams in reference responses is also in the generated response. Common metrics for lexical similarity are BLEU, BLEU, Rogue, Meteor++, TER, TER, and CIDER, CIDER. They differ in exactly how the overlapping is calculated. Before foundation models, BLEU, Rogue, and their relatives were common, especially for translation tasks. Since the rise of foundation models, fewer benchmarks use lexical similarity. Examples of benchmarks that use these metrics are WMT, Coco Captions, and GemV2. A drawback of this method is that it requires curating a comprehensive set of reference responses. A good response can get a low similarity score if the reference set doesn't contain any responses that looks like it. On some benchmark examples, Adept found that its model Fuya performed poorly, not because the model's outputs were wrong, but because some correct answers were missing in the reference data. Figure 3-5 shows an example of an image captioning task in which Fuyu generated a correct caption, but was given a low score. Not only that, but references can be wrong. For example, the organizers of the WMT 2023 metrics shared a task which focuses on examining evaluation metrics for machine translation, reported that they found many bad reference translations in their data. Low quality reference data is one of the reasons that reference free metrics were strong contenders for reference based metrics in terms of correlation to human judgment. Another drawback of this measurement is that higher lexical similarity scores don't always mean better responses. For example, on Human Eval, a code generation benchmark, OpenAI found that BLEU scores for incorrect and correct solutions were similar. This indicates that optimizing for BLEU scores isn't the same as optimizing for functional correctness. So, okay, so here's figure 3-5. This is an example where Fuyu generated a correct option but was given a low score because of the limitation of reference options. So Fuyu's caption was a nighttime view of Big Ben and the Houses of Parliament. The reference captions were a fast-moving image of cars on a busy street with a clock tower in the background. Lit up night traffic is zooming by a clock tower. A city building is brightly lit, and a lot of vehicles are driving by. A large clock tower and traffic moving near. There's a large tower with a clock on it. Um, so the caption is low because it took that additional step and it said this is definitely Big Ben. These are definitely the Houses of Parliament, even though there was nothing in the reference specifically to do that. So because it did a better job and it was able to identify it and caption it the way a human would, it actually got a worse score because none of the reference captions used to grade a store make any mention of the Houses of Parliament or Big Ben. So it almost looks as if it hallucinates in its response. Big Ben, Houses of Parliament, where did that come from? That has nothing to do with this picture. It's all about traffic. It's all about a clock tower. It has nothing to do with the words Big Ben or Houses of Parliament. You got it wrong. But really, it's the reference captions that are wrong. You can't just say Big Ben or Houses of Parliament in the reference captions because then you give away the whole answer. This is the exact ideal, perfect answer you would want, but your evaluation fails because um, because there's no way to uh, because the reference captions are limited. You would give away the game. You would give away the answer if you included Big Ben and House of Parliament in the reference captions, but you can't grade it properly without those in there. So it's just this is an example of um, how evaluation needs to improve. All right, so the next way to measure the similarity between two open texts is semantic similarity. Lexical similarity measures whether two texts look similar, not whether they have the same meaning. Consider the two sentences, "What's up?" and "How are you?" Lexically, they are different. There's little overlapping in the words and letters they use. However, semantically, they are close. Conversely, similar looking texts can mean very different things. "Let's eat grandma" and "let's eat grandma," one with a comma and one without, mean two completely different things. Semantic similarity aims to compute the similarity in semantics. This first requires transforming a text into a numerical representation, which is called an embedding. For example, the sentence, "The cat sits on a mat," might be represented using an embedding that looks like this. So what it looks like is within square brackets, there are decimal numbers to two decimal points. The first is 0.11, then 0.02, then 0.54. Semantic similarity is therefore called embedding similarity. Introduction to Embedding discusses how embeddings work. For now, let's assume that you have a way to transform text into embeddings. The similarity between two embeddings can be computed using metrics such as cosine similarity. Two embeddings that are exactly the same have a similarity score of 1. Two opposite embeddings have a similarity score of -1. I'm using text examples, but semantic similarity can be computed for embeddings of any data modality, including images and audio. Semantic similarity for text is sometimes called semantic textual similarity. Warning: while I put semantic similarity in the exact evaluation category, it can be considered subjective, as different embedding algorithms can produce different embeddings. However, given two embeddings, the similarity score between them is computed exactly. Mathematically, let A be an embedding of the generated response and B be an embedding of a reference response. The cosine similarity between A and B is computed as this equation. So the equation is it looks like it's printed a little bit strange. It's printed kind of on the upper level, as if like an exponential would be printed. I think that's probably a mistake. It's probably due to these long pipes here. I don't think that's how it's meant to be printed. Um, so yeah, so let's go to the AI on this. We can use the quick version of the model. So we'll make a new chat. Yeah, I'll just use 4.0. We'll say rewrite out this equation. Write out this equation. Okay, and see what how because it uses latex, which is the yeah. See, so this is a lot easier. So this represents the Euclidean norm. What the hell is that even? Oh yeah. So let's read this first before we look at that closer. So there's the equation there. I'm not going to read it out loud because it looks like it's written in a kind of an odd way. A times B being the dot product of A and B. Pipe A, pipe being the Euclidean norm, also known as the L squared norm of A. If A is uh, the set of numbers in brackets that I read earlier, 0.11, 0.02, and 0.54. The Euclidean norm of A is equal to uh, each of those numbers squared added to together, and then the square root. So it looks kind of similar to yeah, so the Euclidean norm. Um, Man, this is what the author says. It's okay to just either gloss through or to skip entirely, but I'm going to give it a little bit of an effort. Okay. Okay, so we can see the. All right, well, explain this to me. I'm kind of lost. Okay. Does this have to do with the does this have to do with the quadratic formula? It looks kind of similar to that. So the equation is just finding a length of a vector in 3D space. It uses the Pythagorean theorem. Yeah. No, it looks different. Okay. Okay, the other thing I noticed is it looks a bit like the Pythagorean theorem, but I couldn't tell if it was something that looked more like the Pythagorean theorem or looked more like the quadratic formula. Yeah. Oh, yeah. Okay, so it is based on, yeah, but there's an extra number. Yeah. Okay. So when I thought of the quadratic formula, I was making a bit too big of a leap. My first instinct was the Pythagorean theorem, and that was the instinct that was correct. Yeah. Yeah, I noticed this looks a lot like the Pythagorean theorem, but it just kind of threw me off because it has an extra dimension to it, but that's totally fine. All right, so metrics for semantic textual similarity include BERT score. Embeddings are generated by BERT, and mover score. Embeddings are generated by a mixture of algorithms. Semantic textual similarity doesn't require a set of reference responses as comprehensive as lexical similarity does. However, the reliability of semantic similarity depends on the quality of the underlying embedding algorithm. Two texts with the same meaning can still have a low semantic similarity score if their embeddings are bad. Another drawback of this measurement is that the underlying embedding algorithm might require non-trivial compute and time to run. Before we move on to discuss AI as a judge, let's go over a quick introduction to embedding. The concept of embedding lies at the heart of semantic similarity and is the backbone of many topics we explore throughout the book, including vector search in chapter 3 and data deduplication in chapter 8. So this might be a good stopping point because embedding is its own next subject. We're moving on uh, to learn about something new. Um, so, and this is something that is really critical to. Well, let's finish this off this section because it's very brief, and then end the video at AI as a judge. So, introduction to embedding. Since computers work with numbers, a model needs to convert its input into numerical representations that computers can process. An embedding is a numerical representation that aims to capture the meaning of the original data. An embedding is a vector. For example, a sentence, "the cat sits on a mat," might be represented using an embedding vector that looks like this. And this looks the same as the ones before. It's open square bracket 0.11 comma 0.02 comma 0.53 close square bracket. Here we use a small vector as an example. In reality, the size of an embedding vector, the number of elements in the embedding vector, is typically between 100 and 10,000. Models trained especially to produce embeddings include the open source models BERT, CLIP, uh, con contrastive language image pre-training, and sentence transformers. There are also proprietary embedding models provided as APIs. Table 3-2 shows the embedding sizes of some popular models. Table 3-2 embedding sizes used by common models. Model embedding size. So Google's BERT has a size, OpenAI's Clip, OpenAI's Embeddings AI, API, and the Cohere's embedded V3. They all have sizes, differing sizes. Because models typically require their inputs to first be transformed into vector representations, many ML models, including GPTs and llamas, also involve a step to generate embeddings. Transformer architecture visualizes the embedding layer in a transformer model. If you have access to the intermediate layers of these models, you can use them to extract embeddings. However, the quality of these embeddings might not be as good as the embeddings generated by specialized embedding models. The goal of the embedding algorithm is to produce embeddings that capture the essence of the original data. How do we verify that? The embedding vector that we've been looking at, the .11, .02, and .54, looks nothing like the original text that cat sits on a map. At a high level, an embedding algorithm is considered good if more similar texts have closer embeddings, measured by cosine similarity or related metrics. The embedding of the sentence, "the cat sits on a mat," should be closer to the embedding of "the dog plays on the grass" than the embedding of "AI research is super fun." You could also evaluate the quality of embeddings based on their utility for your task. Embeddings are used in many tasks, including classification, topic modeling, recommender systems, and RAG, retrieval augmented generation. An example of benchmarks that measure embedding quality on multiple tasks is MTEB, Massive Text Embedding Benchmark. I used text as examples, but any data can have embedding representations. For example, e-commerce solutions like Criteo and Coveo have embeddings for products. Pinterest has embeddings for images, graphs, queries, and even users. A new frontier is to create joint embeddings for data of different modalities. Clip was one of the first major models that could map data of different modalities, text and images, into a joint embedding space. ULIP, Unified Representation of Language, Images, and Cloud Points, aims to create unified representations of text, images, and 3D point clouds. ImageBind learns a joint embedding across 6 different modalities, including text, images, and audio. Figure 3-6 visualizes Clip's architecture. Clip is trained using image text pairs. The text corresponding to an image can be the caption or a comment associated with this image. For each image, text pair, Clip uses a text encoder to convert the text to a text embedding and an image encoder to convert the image to an image embedding. It then projects both these embeddings into a joint embedding space. The training goal is to get the embedding of an image close to the embedding of the corresponding text in this joint space. So here's figure 3-6, Clip's architecture. And see this name here, Radford. This is the guy that was swooned after in Situational Awareness by Leopold Aschenbrenner. This is the guy that you'll never see on the Joe Rogan podcast. This is the guy whose ass is in the seat of developing this AI technology and doesn't have time for anything else but that. Alec Radford is an incredibly gifted and prolific researcher slash engineer at OpenAI, behind many of the most important advances. Though he's busy doing that and not other things like going on podcasts and talking about things unrelated to his expertise. So you've probably never heard of him, but he does have He is included in this blog here. I don't know if this is by him, but artificial-intelligence.blog is pretty good because it shows you the people in AI here. If you go to more AI people in AI, these are all the really important people involved in AI right now, and we see the first person listed is Alec Radford. So this is where you can go to get a good sense of like who the big players in AI really are. So number one on the list is Alec Radford. Number two is Ilya Sutskever. So looks pretty good. I've never really heard of Jeffrey Hinton. So this he's a good one to look at next. So really good article because we can see who the really serious published people are. They made it to the front page of this, many with AI generated photos. And it also could serve as a more comprehensive list of all the people involved if you look on the second page. But the fact that Alec Radford is number one is exciting. It lends this site a lot of credibility in my mind. And if you go to AI videos here, you can see we've got AI education videos. It's all in one place. So we got 34 AI education videos. Um, I'm not sure who made this site, but it's a um, site that is pretty comprehensive. So let's look at the AI news. Um, um, so the top story should be on DeepSeek. Yeah, the site obviously looks kind of janky and poorly done, and just about everything on it was done by an AI. Probably a lot of the writing too, but I do like it because it's one of the only sites out there with Alec Radford on its radar. And Alec Radford, you can see, was swooned over by Leopold Aschenbrenner. So, all right. So here's Clip's architecture. Um, yep. So happy hippie hamster. Okay. Then there's the picture of it, image decoder, text decoder, converted into numbers, language projection matrix, vision projection matrix, multimodal embedding of image, multimodal embedding of text, cosine similarity score. A joint embedding space that can represent data of different modalities is a multimodal embedding space. In a text-image joint embedding space, the embedding of an image of a man fishing should be closer to the embedding of the text a fisherman than the embedding of the text fashion show. Although fashion shows these days, you never know. This joint embedding space allows embeddings of different modalities to be compared and combined. For example, this enables text-based image search. Given a text, it helps you find images closest to this text. All right, so now I'm at a better stopping point. AI as a judge. So all of this is getting to be very technical, down in the weeds. But I'm making a lot of good progress. I'm on page 227 already. So yeah, that's it for this video. Well past the hour mark. So thanks for watching and see you in the next one.